final evening of particles, patterns, and purpose. So tonight, string theory and the multiverse and design, and where God fits in. I think probably a brief recap may be in order at this point before we jump into tonight's subject. On the first evening, we talked about the fine-tuning of the constants of the standard model of particle physics. Things like the masses of the quarks and the strength of the forces. And these things seem to be quite finely tuned in order that life is possible. And we don't know of any other reason. The numbers are otherwise arbitrary. And then last week we looked at the so-called standard model of cosmology, the early history of the universe. And there are things like the rate of initial expansion, which is incredibly finely tuned, the size of the earliest fluctuations, which are quite necessary for stars and galaxies to form, but not to collapse into black holes too early. The whole mystery of why the universe is made of matter rather than antimatter, and the fact that at a very early point in the Big Bang there was apparently 1,000,001 quarks for every billion antiquarks, and nobody knows why. And the fact that the universe is accelerating due to what's called dark energy, or the cosmological constant. And people can calculate it, and the number comes out a huge factor too big, a number with 120 zeros. It's very small, it's not zero, it's pretty important, but it's about what it is, and nobody knows why. So these remarkable coincidences, both in the laws of physics and in the early history of the universe, which seem to be finely tuned for life. It should be pointed out that the early history of the universe is probably related to the way the particles interact as well. The two are very much tied together, so that, for example, so far undiscovered laws of particle physics may explain the very rapid inflation which probably took place right at the beginning, but we don't yet know the law. So the way in which the universe expanded, the cosmological constant, the dark energy, all these things are probably related together. So, putting all this together, it looks as though the universe is designed so that life is possible. And again, I quote from Leonard Susskind. He says, "The real mystery raised by modern cosmology concerns a silent elephant in the room, an elephant, I might add, which has been a huge embarrassment to physicists. Why is it that the universe has all of the appearances of having been specially designed just so that life forms like us can exist?" Now you may ask why it should be embarrassing to physicists. I'm a physicist, I'm not embarrassed by these things, but Leonard Susskind is because he's an atheist. It's just rather embarrassing if you're a materialist atheist to be living in a universe which is apparently specially designed for life. So what is Leonard Suskind's solution to this enigma? Well, it's something called the multiverse. What is a multiverse, and why does it explain apparent design? The general idea is that there are a vast number of complete universes, in each of which the laws of physics are different, and they would have had different histories. Now, in a sense, it seems ridiculous to talk about different universes. Surely the universe is the universe, all that is. The point is that these so-called universes are completely separate from each other, and the laws of physics are different. So within each universe, you think you are in the universe. So they've invented this term multiverse, a multitude of universes, to explain this concept. So it's a bit weird. I mean, in normal parlance, the universe is just everything. So we're talking about a multitude of apparent universes, and we call it the multiverse. And each universe has different laws of physics and a different history. Now, the idea is that if there are enough of these different universes, and you vary the laws enough, then just by chance, in one or two of them, it'll all fit. And you'll get the right laws and the right history and life would be possible. But you may say, isn't it extraordinarily lucky that we're in one of the lucky ones? You know, with all these millions and millions, why should we be a lucky universe? Well, the answer is, if it wasn't lucky, we wouldn't be here. We're in a universe where life is possible. Therefore, it must be one of the lucky ones. So that's the general idea of a multiverse. It is also worth saying that there is more than one set of physical theories which gives rise to the possibility of a multiverse. I'm only going to talk about one of them, which is the ideas suggested by what's called string theory and M theory. So I'm only going to talk about this particular method of imagining how a multiverse could come into existence. There are others. So the structure of the rest of this evening is as follows. First of all, what is string theory and why was it invented? Secondly, how does string theory give rise to these multiple universes which might explain design? Thirdly, then, a critique of string theory and its solution to design. And finally, some more general remarks about how to think about God and design in the universe. So, first of all, what is string theory and why was it invented? Well, primarily to solve two problems in particle physics. First of all, the idea of trying to produce a unified model of physics. There are these different particles, there is different forces. Wouldn't it be wonderful to have a single theory, a single idea, a single concept, which united all the different forces and particles to make them seem as one basic phenomenon giving rise to all the other stuff? That's the first attempt that string theory tries to solve. And the second is a more mathematical and technical one. When you do calculations with particles that you really think are infinitesimally small points, you come up with horrible, infinite, stupid answers. In other words, if you really think that the electron is got no size at all, but it's an absolutely point particle, and do some sums on it, you come up with infinite numbers. Do you follow me? And there are a number of problems related to that sort of thing if you really think that particles are absolute geometrical points. String theory is an attempt to try and solve both of these problems. Let me go back to the question of unifying the different forces. We believe that there are four forces that we see in the world. There's gravity, there's the electric force and the weak force, and also the strong nuclear force. The weak nuclear force and the electric force, or the electromagnetic force, they probably are united or become aspects of one phenomenon round about the energy that the Large Hadron Collider is currently investigating. But it would be lovely to see if we could make them all aspects of one fundamental phenomenon. And there are reasons to believe that as you go to higher and higher energies, which in the history of the universe means closer and closer to the Big Bang, then what appear in our sort of world to be separate phenomena might actually appear to be one single phenomenon. It sort of freezes out into different things at lower temperatures. There are some theories called grand unified theories. The unified theory which unifies electromagnetic and weak forces is not very grand. But if you try to unify the strong force, the strong nuclear force, as well as the weak and the electromagnetic, that's called a grand unified theory. And various of these have been invented and none of them work properly. There is no accepted grand unified theory. One major problem, for example, is that they all predict that protons are going to be radioactive and decay. Well, protons don't decay. So far, no successful grand unified theory. But it's worth noting that, in fact, it was the invention of grand unified theories that first led to an idea of inflation. So they have been important. But string theory is even more grand than a grand unified theory. The aim of string theory is actually to unite gravity as well as strong, weak nuclear and electromagnetic. And one thing that string theory particularly claims to be able to do is to produce a quantum theory of gravity. It's proved exceptionally hard to make a theory of gravity, like general relativity, which is consistent with quantum mechanics. Hugely difficult, and string theory aims to do that. So, just to go back to this diagram again, we think that round about the energy of the Large Hadron Collider, the electric and the weak forces may become a single phenomenon. We think if you go up to a factor of a million higher energy than that, very, very high energies, then that's where grand unified theories might work, and the strong force would be the same as the others. And go even higher than that, back towards the Big Bang itself, and gravity might be all united with the rest. The basic idea of string theory is that the most elementary things are not actually points, but little strings, or rubber bands, or loops, or something. They're linear, they're lines rather than points, okay? Or to be more precise, the things that we call fundamental particles and whatnot are actually the different ways in which these strings can vibrate, okay? So that one sort of type of vibration might be an electron, but it vibrates a different sort of way, and it might be a gluon or a photon or something. Do you follow me? So the general idea is that the different ways in which these strings can vibrate would correspond to the different particles and the different forces. So everything would be a product of this single idea of these strings or loops. And there are some remarkable mathematical successes of this theory. Extraordinary sort of mathematical miracles, apparently. Things drop out, which really seems, this is very significant, it seems to work. However, there are at least two big buts. First of all these miracles, all these wonderful cancellations, the infinities dropping out and all that sort of stuff, it only works if you assume that there are 9 dimensions of space instead of 3. We normally work with 3 dimensions of space and 1 of time, space-time. But in order to make these wonderful strings work mathematically properly, you have to assume that we really live in a universe with 10 dimensions of space-time. 9 dimensions of space, 1 dimension of time. Okay? Oh. Jolly good. I thought there's something wrong, but I didn't know what it was. That's the first problem, because we all know we live in a 3-dimensional world, don't we? Second problem is it only works if the universe, the laws of physics, exhibit a very fundamental symmetry, which is very hard to explain, I don't really understand it, but it's called supersymmetry, or SUSY for short. So you have to have these 2 things to make string theory work mathematically. Supersymmetry is an extraordinary idea which actually unites the matter particles, the quarks and the leptons, which are all fermions, with the force particles, photons and gluons, which are all bosons. Fermions and bosons are very different. You can't put 2 fermions into the same state. You can have as many bosons as you like in the same state. They're very, very different. But if supersymmetry is correct, then every particle has another sort of shadow particle, a super partner, which corresponds to it. So, for example, an electron, which has spin of a half and is a fermion, will be paired with what's called a selectron, which has spin 0 and is a boson. A photon, which is spin 1 and a boson, will be paired with a photino, which is spin a half, and a fermion. So all the particles that we know about would be actually paired. These are the particles we know about, okay? The particles of the standard model, the quarks and the leptons and the force particles and the boson, and even the shadowy Higgs boson in behind there. Now, if supersymmetry is correct, then all these matter particles have partners with similar masses, which will be bosons, and all these force particles will have partners, which will be fermions, okay? Now, like string theory, supersymmetry it does solve a number of theoretical puzzles, things that theoretical physicists are worried about. If supersymmetry were true, things would cancel out and it would all work mathematically. So it's a very wonderful idea. It's worth saying that string theory is usually and properly referred to as superstring theory. And that's not because it's a super theory of strings. It's not a very wonderful theory. It's because it's a theory which has supersymmetry built into it. It's basically supersymmetric string theory. Do you understand? That's why it's called supersymmetry. For example, we talked about dark matter. There is 70% of the matter in the universe is something completely unknown. Well, maybe it's one of these supersymmetric particles that no one's seen yet. That's why we haven't observed it before. It's a nice idea. It's worth saying that for many people, the Large Hadron Collider, they thought it would have enough energy to produce these supersymmetric particles for the first time. They were anxiously and excitedly awaiting the Large Hadron Collider firing up and giving showers of these new particles which no one had ever seen before. No supersymmetric particle has been seen yet so far. So basically the Large Hadron Collider is really not dealt a death blow to supersymmetry, but it's quite a serious problem for people who believe in it. Desperately searching for Susie.